Okay, now that we can add whole numbers, we need to look into signed binary numbers, positive and negative values. To represent negative values, computer systems commonly allocate the high order bit to indicate the sign of the value. In the event, or the high order bit is the leftmost bit in the byte, and it's also called the most significant bit. The remaining bits then represent the value of a number. We're going to look at three signed binary number representations: signed magnitude, ones complement, and twos complement. An 8-bit signed binary number that is represented in signed magnitude format, the most significant bit is considered to be the sign bit. And if the sign bit is a 0, if the leftmost bit is a 0, the value is considered positive. But if the sign bit or the leftmost bit is a 1, the value is negative. The lower 7 bits represent the numeric magnitude or absolute value of the signed number. So, for example, in 8-bit signed magnitude, a positive 3 would be represented as all zeros except for the last two bits being ones. Notice that the leftmost bit is a 0, meaning that it's a positive, and then the number 3 is represented in the lower 7 bits. In signed magnitude, the lower 7 bits would be the same, represent the number 3, but the sign bit would be a 1. The addition rules work as before. Our first number is 75 base 10, and our second number is 46 base 10. But if we're doing binary addition, 1 plus 0 is 1, 1 and 1 is 0 with a carry of 1, 1 and 1 is 0 with a carry of 1, then the 3 ones gives us a 1 with a carry of 1, and 1 plus 2 zeros is 1, 0 and 1 gives us a 1, 1 and 0 gives us a 1. Our first two numbers were positive, so is our third number, so our sign bit does not change. In this example, we were careful to pick two values whose sum would fit into the 7 lower bits. If that's not the case, there might be a little bit of a problem. What if the sum magnitude requires more than 7 bits? We could have overflow into the sign bit. In this example, our first number is 107 base 10, and the second number is again 46. But in this case, we end up with an overflow into the sign bit of 1. Here we've experienced an overflow as the last carry into our sign bit, and hence calculated an erroneous result, because clearly adding 107 and 46 won't give us a negative value, but this process would cause our sign bit to be a 1. Some advantages and disadvantages of signed magnitude format. It is easy to understand. The leftmost bit is the sign, followed by the rest of the number. However, to do this requires some complicated computer hardware. And also, this allows for both positive and negative representations of 0. For these reasons and others, computer systems employ complement systems for numeric value representations. The first one we're going to talk about is ones complement, and then we'll discuss twos complement. To negate a number using ones complement, there is only a single step. We invert all of the bits, meaning we change our zeros to ones and the ones to zeros. So the ones complement of 0, 0, 0, 1, 0, 0, 1, 0, or positive 18, negative 18 would be represented as 1, 1, 1, 0, 1, 1, 0, 1. Notice each of the bits has been transposed into its opposite value. Negating again, or inverting the bits again, via ones complement would take our negative 18, and a negative 18 would return again back to a positive 18. This procedure alleviates the issue of overflow into the sign bit. However, it does still leave us with both positive and negative representations of 0. We can have all ones or all zeros to represent 0. So then we have the 2's complement, which takes care of that problem. With the 2's complement negation, you invert the bits, or take the 1's complement, and then you add 1 to the least significant bit. Same example, we take our 18, and we invert the bits, but then we add 1. This would be our representation of negative 18, 1, 1, 1, 0, 1, 1, 1, 0. If we negate again, meaning if we invert the bits again from here to here and add 1, we end up back at our original value of 18, or 0, 0, 0, 1, 0, 0, 1, 0 in 8-bit binary format. Negating then allows us to subtract. And remember, subtracting is the same thing as adding a negative. So for the first step, we need to negate our second number, or the number to be subtracted. And we'll do this in 1's complement subtraction by, of course, taking the 1's complement. We will then add our negated second number to the first number, or the number to be subtracted from. And if there is an overflow, a final carry equal to 1, then that means that the answer is positive. And what we need to do then is to add the overflow to the least significant bit. This is referred to as an end-around carry, and adding that 1 to the least significant bit will get us our magnitude result. However, if there is no overflow, or if our final carry equals 0, this means that our answer is negative. And if our answer is negative, we must take the 1's complement to get the magnitude of the result. So our first example, we're going to subtract two binary numbers. This happens to be 51 minus 5, so we're expecting to get a result of 46. First, notice the number of bit positions and the number to be subtracted does not match. We'll want to add leading zeros so we have both numbers in 8-bit format, because changing 101 to 010 is a lot different than changing 000000101 to its 1's complement format. So we take the 1's complement of our second number with the leading zeros, and then we add that to our top number. When we do that, we find we get an overflow of 1 from our most significant bit position, which is good because we're expecting a positive number, and that will indeed mean that it's positive. So what we need to do then is to add that 1 to our least significant bit, the end-around carry, to get our magnitude. If we were going to add these numbers the other way around, we would still negate the second number, 5 minus 51. So if we negated our binary 51 using 1's complement, we would find there was no overflow, meaning that our answer is negative. Given that the answer to this problem is negative, we must take the 1's complement to get the magnitude of the result. 2's complement works in a very similar manner to the 1's complement. We convert the number to be subtracted by taking to a negative by taking its 2's complement this time. We still add the result, the negated number, to the number to be subtracted from. But this time, remember, 2's complement already adds 1 to that least significant bit, so this time if there's an overflow, a final carry of 1, it still means that our answer is positive, but we can, for positive results, we can ignore the overflow, and the remaining bits are going to be our magnitude. If there is no overflow, if our final carry is 0, then our answer is negative, and then we have to take the complement, in this case 2's complement, to get the magnitude of the result. So for our 2's complement subtraction example, step 1 is to take the 2's complement of the second number. Again, don't forget the leading zeros. We add the 2's complement to our first number. We have an overflow, meaning it's positive, so we ignore our overflow to get the magnitude of a result. Subtracting the other way around and choose complement. The process is the same, but this time we have no overflow, meaning that our result is negative, and so we have to take the 2's complement to get our result. At this point, please complete the project for computer math and the associated discussion.